Hey guys, it's been a minute, huh? I'm gonna take a quick, no more than 4 minutes to review, and that's because at 4 minutes I will have reached the end of my free subscription to make this video. So it'll be short. Before we went on break, I had you guys do a reaction where we graph something, the temperature change. A lot of times, certain reactions, particularly ones where we involve solutions, don't have a lot of visual clues for us. So we use things like indicators and thermometers to tell us when a chemical reaction has occurred, especially when we have something like this, where we have an acid and a base. This is something called a neutralization reaction, and one of the defining characteristics of a neutralization reaction is the formation of water and a salt. Probably not talk much more about it ever again, but what you have to know is that sometimes the products aren't a gaseous material, and so it's hard to tell when a chemical reaction has occurred. I think it was about 2 weeks now ago, I had you guys add something called 1 molar sodium hydroxide and 1 molar hydrochloric acid together. What we did was we started with a small amount of base and a large amount of acid, and we kind of increased 1 by 5 while decreasing 1 by 5 until we got this sort of cascading step function. This tells us a lot of important stuff. I know this graph looks really, really busy, but it's not. What's important is for us to be able to take a piece of information that displays graphical data and extract some key information from it. And that's something that you're going to have to do, I don't know, for a long time, well after you're gone out of ISM. Here's what this data tells us. Let's look at the first data point here. When I have a little bit of base with a lot of acid, I had only a 2-degree temperature change indicated on this second right y-axis. Now that's a chemical reaction because the temperature has changed. It's not very much. What it really says is that given this ratio of reactants, I did not see a very drastic temperature change, which must mean it's not very efficient. There could be wasted unreacted material that I just throw down the drain. You might not always want to do that. At the highest point, with a temperature change of a whopping 28 degrees, which is actually a lot if we're talking about Celsius, what we can see is that at 20 mils of base and 20 milliliters of acid, I saw the greatest change in temperature, which tells us that I had the greatest reaction at that level or at that installment of my reactants. Now, it might not always be 1-to-1. You could have different bases and different acids that react in different ways, and that gets into a whole other branch of chemistry where we calculate and predict reactions. Much more on that later in your life. For now, let's just stick with the simple basics here. I could see the greatest temperature change at equal amounts of acid and base. Now, you might use this information later. We could do a lab, perhaps maybe some point next week, where I just give you two random amounts of stuff and I say, hey, figure out what the best combination of reactants would be in order to get the greatest temperature change, or what the most efficient reaction would be, and you'd have to graph that data and generate something similar to what we've shown right here, where maybe we increase 1 by 5 and decrease 1 by 5 until we can get to the optimum change in temperature, which would tell us the best combination in terms of volumetric additions of both of my ingredients. So we're going to use this video to help answer some questions, and we're also going to use this video to help us construct a lab, maybe without a procedure at all, where you just have to say, oh, I got to add these two and see which gives me my greatest temperature change.